modes of reaction isotherm, and in this isotherm there is a relation between Gibbs free energy, standard Gibbs free energy, temperature, and your reaction quotient or pressure quotient. In this case we have taken the pressure quotient here. So we'll start with taking a reversible reaction. Let's say we have taken a general reaction A plus B plus so on to give XX plus YY plus so on. Now the smaller alpha vats are the stoichiometric coefficients of the reactant and products. If we have to find out the change in Gibbs free energy of a reaction, it is given by Gibbs free energy of product minus Gibbs free energy of reactant. And since the absolute value of Gibbs free energy cannot be calculated, so we take the Gibbs free energy in terms of the chemical potential here. This we have already studied in our previous class, so I'm not going to explain it here. If any one of you have a doubt, you can go to the previous class. Alright, so I have put Gibbs free energy in terms of the chemical potential here. Here mu x, mu y, mu a and mu b are chemical potential of x, y, a and p respectively. Now we have also studied this relation in the previous class where chemical potential has been written in terms of standard chemical potential and partial pressure of the species. So it's mu is equal to mu naught plus RT ln P. So if we have to write the chemical potential of all the species, that is all the reactants and product, we can write them in these ways as we have written in the third equation. And after putting the values of chemical potentials from third equation to our first equation, we get this equation where delta G is equal to x is stoichiometric coefficient of your product x into chemical potential of x plus y into chemical potential of y plus so on minus that of the reactant. Alright. Now if we manipulate this equation, or you can say we rearrange this equation, we can get the fourth equation. I'll tell you how I have written that. I have taken only the chemical potential terms first and written them separately. Here should be a capital E. So writing the chemical potential terms first, we get this. This is nothing but equation of delta G naught. Delta G naught, that is standard Gibbs free energy. If you see the relation here, it's for Gibbs free energy in terms of chemical potential. Similarly, when you have standard Gibbs free energy, you get a similar relationship, but instead of chemical potential, here you have standard chemical potential of the species. So in the next equation, what I have done, I have replaced this underlined term, these underlined term by delta G naught, where delta G naught is your standard Gibbs free energy. Alright, and this term, how I have written, I have taken the log terms separately and I have applied two formulas of log. Which two formulas? I'll write them here. If you have log x plus log y, so you write them as log x into y. Alright. And if you have a, l and x, then the formula becomes ln x raised to the power a. So by using these two formulas, I have condensed the log terms to write it as this: RT ln px raised to the power x into py raised to the y, and so on for all the product terms divided by that of the reactants. It's Pa is partial pressure of A raised to the power stoichiometric coefficient of A, that is small a, into PBB and so on. Alright. Now in the fifth equation, if you see what I have done, I have written this bracket term has been replaced by QP. this QP is your pressure quotient. Here I have written it. QP is equal to the ratio of partial pressure of your product raised to their stoichiometric coefficient divided by product of partial pressure of reactant raised to their stoichiometric coefficients. Now some of you might have doubt from the previous class where we have written Kp is equal to partial pressure, product of partial pressure of your products divided by partial pressure, product of partial pressure of your reactants. This derivation you have done previously. So some of you might have a doubt that why instead of Kp we are writing Qp. So I'll explain why. When we were writing this, it has a condition of equilibrium. At equilibrium, your Kp is equal to this, or you can say your Kp is equal to Qp. But throughout the reaction, this ratio of product of partial pressure raised to their stoichiometric coefficients of products divided by reactant is given by Qp. Alright, and this Qp under special condition of equilibrium become Kp. So don't get confused between Qp and Kp. This is when your reaction is not in equilibrium. Alright. Okay. So this I have replaced by Qp in my fifth equation. So this is a form of your bond of reaction isotherm. Now I have further given you something. We have already established this relation delta G naught minus RT ln Kp. Alright. So this value of delta G naught, if we put in the fifth equation, we get a relation delta G is equal to minus RT ln Kp plus RT ln Qp, and we can further condense the log terms and write it as delta G is equal to RT ln Qp divided by Kp. So these are the various different forms of your bond of reaction isotherm. And if you see, like in the previous class, what we have done, we have established this relation. This relation you can also derive from this equation. If you take equilibrium condition for this reaction, what will happen? Your delta G will become 0. Under equilibrium condition, we have studied that our delta G is 0. So you put 0 here, your delta G naught will be here, plus RT ln, this Qp will become Kp under equilibrium condition. So what kind of equation you will get? You will get an equation like 0 is equal to delta G naught plus RT ln Kp. And if you rearrange this equation, you will get delta G naught is equal to minus RT ln Kp. So this can be derived here using the same equation. Alright. So we have three different kind of bond of reaction isotherms.